Okay, so this is section 12.5, and the main motivating question for today is how do we compute triple integrals and what are some applications? So we're just going to do a nice comparison between what we've already learned with double integrals and how it extends to triple integrals. And so what I'm sketching, or what I have pictured here, is just the region that we integrate over. We were typically calling that the region R when we were doing double integrals. And so we were chopping it up into little sub-rectangles. And they had area delta A. And the analogy, so this is the area of one of these little regions, which was just delta x, delta y, or we could switch and do it in terms of polar or one of our general UV coordinate changes. The analogy now for a 3D region, this is my 3D region E, is now I'm going to chop it up, not just into sub-rectangles, but into these rectangular boxes. And so each of these is just going to have a little volume. This is volume of just one of these little boxes, delta V, and that's now going to be delta X, delta Y, delta Z, if I'm doing this in Cartesian coordinates. And then we defined the actual double integral as this limit of this double Riemann sum. And what's going to happen now when I do a triple integral is I'm now going to be integrating over this region E, and I'm going to be integrating now a function of 3 variables. And we're going to use dV for my volume element instead of dA. And this is now going to be the limit as delta V goes to 0, which would mean n going to infinity, m going to infinity, and I guess we'll say and p, because now we're going to have 3 sums. I'm just going to put it as I, j, k, and you can just imagine they have upper limits that are all going to infinity. X, I, y, j, c, k, delta v. So let's look at some applications and compare them for double integrals versus triple. So we learned that if I just have an integrand of 1 over here with a double integral, then that's the equivalent to chopping up this region here into a bunch of little sub-rectangles, adding up the area of all those rectangles, taking the limit as they get smaller and smaller, and that's going to give me the total area of the region. And so similarly, if I were to chop up this region E into a bunch of little rectangular cubes like what we have up here and just add up those red volumes over that entire region, and I take the limit as I chop it up into more and more of those little cubes, it's going to lead me to the total volume of that whole green region. So volume. And similarly, just like we could find mass, if I give you the density now of this green blob, and it would be a function of x, y, z, my units in this case would be units of mass per volume, unit volume, as opposed to over here, if I'm just giving you the density as a function of x and y, my units would be mass per unit area. Okay, and so in this case, if I give you mass per unit volume, then to find the total mass, you're going to be integrating that density with a triple integral. And similarly, this means we can get analogs for center of mass. Instead of just x bar, y bar, and z, and instead of just x bar and y bar, we're now going to have x bar, y bar, and z bar. And so you can guess this is going to look very similar to what we did with double integrals. My denominator is still going to be dividing by the mass. Now my numerator is going to be a triple integral over the region, and I'm still going to have the same integrand, dv. And here I'm going to have, again, this is the weighted density. So y bar will be y times the density, and z bar will be z times the density, dv. And then lastly, we can look at analogies of average value. If I wanted, let's say, the average temperature over that whole green blob up above, I can find it now with the triple integral. And so the analogy is now I'm integrating this function, and now I'm dividing, instead of over here where I was dividing by the area of the region R, now I'm going to be dividing by the volume of my region E. So that's just volume of E. All right, and then to evaluate, remember we had a double integral, we used iterated integrals, and we were able to either slice this up by slicing parallel to the y-axis first or slicing parallel to the x-axis first. Now that I have a triple integral, we're also going to use iterated integrals, but now I'm going to have 6 different ways that I can slice this up. And you can just see as you start to do, I can do dy dx dz, I can do dy dz dx, I can do dz dy dx, dz dx dy, dx dy dz, etc. So let's examine how we can actually set up our limits of integration given one of these orderings. Okay, so let's look at how we will set up our limits, and I do want to make one change to the notes here. Let's just call this function h of xyz, and the region we're integrating over is E. So let's suppose we're going to do the ordering dz dy dx. I want you to visualize what that's going to look like, and then think of how we can find the limits. So if we're doing dz dy dx, then we're holding x and y constant first, and integrating first with respect to z. So visually what that looks like is that we would be shooting an arrow parallel to the z-axis and looking at where it enters and exits our region. And notice, depending on where I shoot that arrow, it's going to enter and exit at different points. In fact, in this case, it's entering always on this surface. Z is f1 of x and y, and it's exiting always on this surface. So we'll do our inside limits first. It's entering along that bottom surface, exiting along the top surface. And my integrand is just going to stay the same here. And so this integrand, this could represent, for example, density, or it could represent temperature on that region if I was trying to find something like the mass or the average temperature. And here's dz. Okay, and then let's say we were going to do dy dx. Okay, and now to find the outer limits for both of these here, I'm going to be looking at my shadow r on the xy plane. So as if you're standing, what I mean by shadow is if you're standing right up here at the very top of one of these arrows parallel to the z-axis and you're looking down, what is the shadow of this region on the xy plane? And so we can see for this particular one that it looks something like this, and this is just in the xy plane. And now to determine these limits, I'm going to be doing exactly what I was doing for double integrals over a region like this. So let's suppose that this bottom function here was g1 of x, and suppose that this top function is g2 of x, and then since I'm trying to integrate next with respect to dy, I'm going to shoot an arrow parallel to the y-axis and look at where it enters and where it exits my region. Okay, and just to show you or remind you, this means to get these first two integrals, you're actually just thinking of as if it was just a double integral, how you would set up your limits for that particular region. So here I'm entering the region at g1 of x, I'm exiting at g2 of x, and then to get my outer bounds, just like we did with double integrals, I'm looking at the smallest and the largest values of x in this region, and my outer limits are always going to be constants, always still here. Okay, and then typically, looks looks like something came off here. Let me, g2 of x, there we go. Typically, you'll see we don't usually write these x equals, like usually you'll just see it as ab, and then you'll just see some function of x here, and you'll just see some function of x and y here. But I'm going to encourage you to keep writing this x equals y equals z equals until we get really good and used to all these integrals, because it really does help with your computation. Okay, so then to actually calculate it, you're going to do exactly what we were doing with double integrals. You're going to freeze, start with the innermost integral first, in this case, integrate with respect to z. So I'm thinking of both y and x as a constant. And then once I've completed that whole integral, only x and y should remain. And then I can freeze x for the middle integral because I'd be integrating with respect to y. After that, only x should remain. And then lastly, after I finish all of these, I should have a number, no x, y, or z, because this represents, this could represent, for example, the mass of that region, or I could be using it in the numerator to find my average temperature. So let's try this with a real example now.